This is an RNZ podcast.
Kia ora and welcome to Elemental, a podcast from RNZ marking the International Year of the Periodic Table. I'm Allan Blackman from the Auckland University of Technology.
And I'm Alison Ballance. And Alan, I have a bone to pick with you and your chemist friends about this bit of the periodic table. We are slowly grinding through the many elements whose names start with the letter T.
Indeed we are.
And they all sound the same. Tellurium and terbium. Thallium, thorium, thulium. Could you lot not have thought about how confusing that is to us mere mortals?
Well, you sounded a bit like Tom Lehrer there in his famous Elements song.
I like that song.
Yes, it's very, very good. Well, I don't know. Who do we blame for this? All of these Northern Hemisphere people who named these things, I guess. I don't know. But yes, they do sound rather similar, but I can assure they all are very, very different. And yes, indeed, episode 86's element thulium does sound a little bit like two preceding it, thallium and thorium.
Yeah, let's just do that again. Thallium, thorium, thulium. Go on, remember those, everybody.
Okay, so Thulium. It was named after Thule, and this was the mysterious far north location mentioned in Greek and Roman literature and which appeared on their maps.
So, what is this mysterious element named after a mythical place?
Okay, vital statistics. Elemental symbol Tm, atomic number 69, that makes it a lanthanoid, and it was discovered in 1879. It's a lanthanoid, and in fact it is the least abundant of all of the lanthanoids, with the exception, obviously, of promethium. But this means that there's still more thulium in the Earth's crust than both bromine and iodine. Very interesting. And of course, as it's a lanthanoid, my goodness, we've gone through this a lot on Elemental. This, of course, means that it took a while to be extracted from the other lanthanoids, in this case, a sample of impure erbium. And this was achieved by another Swede, Per Theodor Cleve, in 1879. Yeah, speaking of taking some time, we've got a story here, but I'm going to preface it by talking about things that you read on the internet not always necessarily being true. Now, the story that I'm about to tell you is given obviously incorrectly in many references on the internet, and this is actually attributed to an entirely different person. So very, very interesting. You've got to do your research and make sure you're right when you're talking about these sorts of things. Anyway.
So you're about to attribute this to the correct person.
To the correct person. Okay. So
Good on you.
It does say on the internet that what I'm going to talk about was actually achieved by a guy by the name of T.W. Richards, who won the Nobel Prize in Chemistry in, I think, 1914 from memory. But in fact, this achievement was carried out by the English-born Charles James of New Hampshire College. What he wanted to do was to determine the atomic weight of thulium. So in order to do this, he needed an absolutely pure sample of a thulium salt. And the one that he chose was a thing called thulium bromate. And 15,000 recrystallizations later, he had his sample.
Let's just be clear, 15,000 recrystallizations.
And if you don't know what a recrystallization is, this is dissolving your sample up in a solvent, usually water, cooling it down, having it crystallize out, and doing it all again and again and again. And at some stages during this particular process of these 15,000 recrystallizations, he could only carry out one or two of these per day, which does give you some idea of how long this must have taken.
Now, quick mental arithmetic, tick, tick, tick. By my calculations, if he's doing it twice a day, every day for at least 20 years it's going to take him. No holidays, no days off. That's some dedication, isn't it?
Yes, indeed. He published the results of this work in a 1911 paper in a thing called the Journal of the American Chemical Society. All you chemists who are listening to this, go away and read it. It's absolutely fascinating stuff.
So does this element have any uses?
No. It doesn't really have many uses at all. So I was struggling for things to say about this. We start with the fact that if you irradiate non-radioactive Thulium-169 with neutrons, you can form radioactive Thulium-170, and that can be used in portable X-ray units, which is kind of nice. And one more, a compound of thulium is apparently used as an anti-counterfeiting device in euro banknotes because it fluoresces blue under UV light.
Now, I'd like to point out, because he shared this with me, listeners, that Alan goes to great lengths to get his facts straight. So, he wrote to the European Central Bank with the following email. Quote, I have read on the internet, we've already heard about the internet this time, that thulium compounds, along with those of europium and terbium, are apparently used as anti-counterfeiting measures in the euro banknotes, owing to their fluorescent properties. Brackets, thulium fluoresces blue, close brackets. However, I can find no definitive references for this, and I'm loath to say something that I don't know to be a fact in the podcast. Thanks for that. So, would you be able to confirm that thulium in some form is used in euro banknotes? End quote. And what did they say, Alan?
Well, they would neither confirm nor deny this.
Which, if you're in New Zealand, you probably understand the hilarity of that. But if you're not from New Zealand, back in the 1980s, New Zealand had a bit of a thing with American warships visiting with nuclear weapons on them, and the American government would neither confirm nor deny whether their warships were nuclear, so we just banned the whole lot. But anyway, this is what the European Central Bank wrote back. Dear Professor Blackman, thank you for your email and your interest in the euro banknotes. I think they were feeling very suspicious at this point.
Yeah, I reckon, yeah.
You can find all information available for the public on euro banknotes and their security features on our website and or in our own respective publications, which don't mention anything about thulium because I looked them up. Back to the letter. For security and confidentiality reasons, we cannot provide further information. Please note that there are a number of chemical elements and compounds which may be found in euro banknotes. Not all of them necessarily serve a specific functional purpose.
Yes, I think she's got a future in diplomacy, the lady that wrote that return email. So basically we drew a blank there, but we did find that the use of europium for red and terbium for green, as well as blue thulium as security features on euro banknotes, is indeed referenced in a textbook on photochemistry. And that wonderful journal Nature Chemistry has published an article on thulium which does include that information, and so we'll take those as today's citations.
Other than the complete cloak of secrecy over its use in euro banknotes.
Over its alleged use.
Alleged use, sorry, yes. Thulium does seem to be otherwise a most unremarkable element.
Well, yeah, one of the books that we use as source material states that, and I quote, there is nothing unique that draws one's attention to thulium, while the same author also stated that thulium is, quote, the least significant element there is, unquote. Hardly glowing endorsements.
And where do you stand on thulium, dear Professor? And I'm thinking, of course, on your recent Nature Chemistry article, written with Rebecca Jelly, the most boring chemical element?
Well, of course, we ended up settling on protactinium. If one element could be said to be the most boring, that could be the most boring, but thulium was a close second. But of course, as we say in the paper, none of them are boring at all, okay? So we decided actually that Charles James's heroic recrystallizations elevated thulium just above protactinium.
Well, talk about looking on the bright side of dull chemicals, Professor. Never a dull moment with RNZ Elemental, eh?
And who knew that we could talk for so long about something so inconsequential? You can find all our episodes, both long and short, at rnz.co.nz/chemistry and at your favourite podcast app. Until next time, I hate to break the news to you, Alison, but we are still in the teas and up to 10. Until then, it's goodbye from me, Allan Blackman.
And me, Alison Ballance. Cheerio, kia pai tō rā.